Let me give us a little motivation. Then I'll try to show us why things are going to work the way they will work, and then we'll finally get to the actual thing, and then it'll probably be time to go. That sounds like a lot, Jeff. We'll see what happens. So motivation is good, even if you aren't an actor. Everything we've worked with so far has been a function. In fact, very often we've called them f of x, g of x. That implies that it's a function. And who remembers what that means? In order for a relation to be a function, what must be true?
Has
to pass the horizontal line test. I like it. Well, that's to be 1-to-1. So let's try again. It has to pass the vertical line test. It's a more basic test. Just to be a function, period, you got to pass the vertical line test. So calculus shouldn't care about that. Calculus itself should not give a shit if something's a function or not. So what do I mean? I mean, if I draw, now obviously if I draw this, that's a function. Does it have a slope everywhere? Yes, right? There's no weird, if I did this, a little kinky, there's no slope there, but everywhere else it's got a slope, right? So just because a function, a thing that, it looks great, oh shit, oh man, it was doing great. Isn't there still a slope everywhere?
Yes.
Yes. So we need to expand what we're able to work with, because this has a slope everywhere. It's got a slope, so I should be able to apply all the calculus we've done. Even though I can't solve this for y, I should be able to still do it. So that's the motivation. Now let's talk about why things are going to work the way they will. So real quick, if I had this equation, it's good. That's creepy. I don't care. It's yummy. It's a yummy equation. Can you solve that for y? If you can, I want to be my master. I will follow you. Can you solve that for y? Can you guys see y and x and everything? They're just two intertwined. You guys understand? There's no way in hell, because you're going to have to take an inverse sine to get that y out of there. Just make sure you guys understand it's all in there, right? But once you do an inverse sine, then everything else gets caught in it. Shit, and you got to do a natural log here to get that y down, and then everything's caught. There's no way in hell to separate the x and y. Are you guys with me?
Yes.
And whenever you can't do that, the thing you're working with is not a function. Okay, maybe. Okay, so that's what I mean by that. If I could graph that, it would look something like that. Some spirography thing, right? Okay, so that's the kind of thing I'm talking about. This is a relationship between x and y, but it's not a function of x or y. So, how are things going to work? And then we'll start to tackle these kind of things. Somebody help me out. What's the derivative of this?
7 multiplied by 3x squared plus.
Yeah, so right, because primarily what is it? What's the outside function?
It's
7 power.
7, yeah.
Right, so the 7 comes down in front of this,
Multiplied by 6. That's 6.
multiplied by the derivative. Let me just stop. You would keep going, right? That's not done. You would keep, but screw it. I'm going to stop right there for a second. What if I would have said instead, this totally different thing, tangent of x plus e to the x to the 7th power. How would you do that, guys? You can do it, Jeff. How can you do that, guys, derivative? 7 times tangent x plus e to the x to the times the derivative of the inside. Are you with me? So what if I had u of x to the 7th power, some function of x in there? How would you take its derivative? Well, I mean, it doesn't matter what I put in there. The next step is always the same, right? It would be 7 u of x to the 6th times u prime of x. I like it, right? And then you would do it if you knew what u was. So in these cases, we call these explicit derivatives because I can see what's going on. This is like the National Geographic thing where the thing drags you behind a bush. This is implicit. It's implied that this is a function of x. I can't see what it is, or I don't know what it is, but I still have to do chain rule for this, right? If the inside thing is a function of x, I have to do chain rule. Are you guys with me?
Yes.
So, y is a function of x in general, right? Not always, but if it doesn't say otherwise, I'm going to just have to assume that. You guys with me? Or some function, some relationship with x. So if I had to do this derivative, which really means, now let me write this better. This is d dx. Right, when I write prime, I pretty much mean by x. If there's any other variable, I should be more explicit by using this notation. So everybody cool? Everybody remember f prime? I could write that as d dx. The derivative of f with respect to x. Okay, cool. Maybe. Y is a function of x, just like u was a function of x. So how would I take this guy's derivative? What would it be? 7. 7?
Or y prime. 2, 6.
Don't finish that part, all right? What was the same every time? 7 blah 6. 7 blah 6. 7 blah 6 times dy dx. That's chain. That's implicit. It's implied that y is a function of x. Therefore, I have to multiply by the derivative. If it turns out that y is x, why is this not wrong? If y is x, dx is 1. It's still right. It's always right. If I don't know what y is, though, I just got to cover my ass. Maybe it's not x. Maybe it's 2x. Maybe it's tangent x. I don't know. Shit. Okay, maybe. I assume you guys like, go on. Okay.
I'm intrigued.
All right. Let's not do that one yet. Let's start off a little nicer. That one looks gross. So here's how this works. It doesn't matter, John. Now this one you can actually, it would be less difficult to solve this for y, but some of you guys just looking at it, you can tell it would, some of you guys might think it's impossible, but it would certainly be ugly to try to solve this for y. Are you guys in agreement? Mm-hmm. Do you concur? Yes, okay. So what I'm about to do is something we've always done. In fact, let me take a step back and make sure you understand. If I give you y equals, like we had earlier, well, if I give you y equals x cubed, I said take the derivative, what would you do? What would you put over here? Oh, you take the derivative of that side and the derivative of that side. Is that cool? You can't do something to one side and not the other. Let me save myself. Okay. So I'm going to do the derivative. What is this? Product rule. It's x times a function of x. They just didn't tell me. If they would have told me y is tangent x, I would have put a tangent x there and I would have put a tangent x there. You would be. They just haven't told me what y is yet. I want you guys to look at this. So how would I take this guy's derivative? What would the rules say? It would be dx dx y plus x dy dx. Is that cool? We just want to get more used to now the other notation, just to be really clear, because we're about to get into the next section, which would be taking derivatives with respect to time, everything. So we're going to be doing d by dt, being very explicit in the derivative we're doing. Minus, now this one I could just do, right?
3.
2y dy dx. So basically, kind of a shortcut is anytime you actually take the derivative of a part that's got a y in it, you're going to tack on dy dx. Because it's going to have to be a chain rule. And now what can I do? Get dy dx by itself. So I'll know exactly what the derivative is. Even though I didn't even know what the freaking function was in the first place. It's not even a function. I can still solve for dy dx. It's just that my slope is going to be dependent on both x and y. Stay with me. So how do I get dy dx by itself? I have to do what first?
Move to one of those.
Get everything with dy dx in it on one side. So I'm just going to switch these out. Is that cool? So we do it not in blue. Blue's kind of hard to see. Let me move up here. Oh, I want to keep you up there. We're going to do you in a second. That sounded weird. All right. You'll get over it. So let's see. No, we're not doing that yet. dy dx. Oh, no, it is dx here. So it's 1y plus x dy dx. I'm going to move these. Is that cool? Add 3, subtract this. So I get all my dy dx stuff on one side. Anytime you have more than one of the variables, so more this is what you do first. Get them all on one side, and then you can... Pull it up. All right. Can you? I got to move the y also, don't I?
Yeah.
Good. So subtract y, subtract y. Bam. So now I can take out dy dx, and what's there? And then I can divide by what I don't want. That's my derivative. That is very different than what we're used to. So if I needed to know at a certain position on this relation, notice I have to talk now. If I graph this thing, who knows what the hell it's going to look like. If I want to know what the slope is at a certain position, I have to be given the entire point. Yes, sir?
How are you able to subtract y from 3? There isn't a lonely y there.
Say what?
We had to get the y.
Yeah, dx is
Oh, right.
1, and then subtract the y.
Yeah.
I like it.
The notation kind of confused me.
I'm with you. And normally you wouldn't even write this, but I think I was just being overly explanatory. All right, maybe. And let's do this before we tackle the ugly one. Let's dial it back. Let's look at a circle. A circle is the easiest thing that's not a function that's very close to being a function. Because I want you guys to really buy into this. So give me the equation of a circle centered at the origin with radius 2.
X squared plus y squared equals 4.
Yeah, there you go. Center of the origin, so it hasn't been moved anywhere. Radius 2, so it's 2 squared is 4. Right? Good old Pythagorean theorem is where that comes from. So let's do this the new way. How do I take this guy's derivative? 2x.
2x
Plus
plus 2y dy dx.
Equals 0. I like it. We stopped there for a second. You guys with me? Derivative of something squared is twice that thing times the derivative of it, the inside. Right? Okay, cool. And then, of course, I immediately do what? Subtract 2x, kill the 2's. Subtract x, and then divide by y. Is that cool? That's kind of nifty. So this is a circle at the origin, radius 2. So I'll laugh at Jeff's attempt at a circle. For me, that's really good. But, oh well. All right. So what's that saying? That means like, let's see. Well, there's no real nice ones on this thing, but what should the slope be here at 2, 0? The slope should be undefined, right? It only rises and never runs. So rise over 0 is undefined, or infinite if you want to say that way. Sure enough, if I plug a 2, 0 in, what do I get? Undefined, right? 2 over 0, undefined. I like it. Okay, good. So what about this point here? What point is that?
1 and 2. Some number.
Come on now. How do you figure it out? You plug a 1 in maybe? Right? Yeah, this one is plus or minus in general, but this one is a positive one, right? So what would the slope, now the slope should be what here? What's the only thing we know of? It's definitely in between 0 and infinity. Ooh. More specifically, it should be negative. So if I plug in the point, now this is why I wanted to do one that we could really get some points, because if I plug, to get this derivative, I've got to plug an entire point in. Because what's the derivative built on? X and y. That's one of the main differences between what we're doing before and what we're doing now. To be honest, the rest of it is actually the same thing, just looks different a little bit. So when I plug that in, what do I get? So the derivative at this point is...
So minus 1 over square root of 2.
I like it. right?
And minus square root of 3.
Minus square root 3 over 3. I like it. Now, if I would have done the unit circle, that would have been a little more interesting because you would have. But I mean, what does that look like?
That's one of the trigonometric.
Yes, it looks like tangent, doesn't it? Holy shit! Anyway, tangent is y over x, isn't it? Weird. And tangent, this is the what?
Tangent line.
Tangent line. Holy shit! Look how it all kind of comes together. All right, so just to show you a slightly different way to look at this, can I solve this for y?
Yeah.
Yes, sort of. What would I get if I solve it for y? I'll get subtract x squared, take a square root, which means I have to put what?
Plus minus.
Plus
Yeah. I like it. Can you guys take that derivative? Take the derivative of the positive one. Do it. Yes, cool.
Negative 2x over
Don't tell me how to do it. Do it. I know that. It sounds like it should be from somewhere back. No. Put it in the same notation. Much better, right? 1/2. It's going to be times negative 2x, right? When you do the chain rule, is that cool? So it's going to become negative x over square root of, right?
Yeah.
And if y is the square root of 4 minus x squared, then what's this? That, right? So when you're able to solve for y, we were able to solve the y up to a point, so I can do the whole thing we just did again with the negative one and plug it in and you go, ooh, look at that. But if you're able to solve for y, sort of, then you're able to kind of check yourself. But not every relation in the world, in fact, most of them, you can't solve for y. They're too intertwined, and the thing looks freaky. How freaky does this look? Not really. You could graph the top part, which is a function, and then you can go and graph the bottom part, which is a function, right? And you can actually put it in your graphing calculator. The one that I erased, shit. The one that was up here, you can't put that in your graphing function in your graphing calculator directly. When we get to parametric equations, we might be able to. Okay. What was the last thing? Oh, they do have a problem like that. Example 1 is a circle kind of problem. Blah, 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 blah. Oh, all right, so last thing. Was that the last thing? Too bad. So how would I figure out if I had this? Actually, let's do, no, let's screw it. We'll do this out of words. How to figure out that guy's derivative. Let me help you out with that.
It's just an angle.
It's a function of x in its own right, is it not? That is a function of x. So I agree, the output for any input that works, this domain of course is restricted, but any input that works, then the output is an angle. But it's not a constant, it's going to change on x, right? So it's not a constant.
So you sign both sides.
Good, I love it. So based off of what we just learned, I can sine both sides. So I get sine y equals x, and now I can just take its derivative. See, now we got this. Now this whole idea of implicit differentiation is a powerful tool. We know what the derivative of e to the x is. We can now use it to figure out what the derivative of ln is. Finally. If I know any derivative of a function, I can immediately find its inverse derivative by applying implicit differentiation. Oh shit. So how does this work? What's the next? How do I take this guy's derivative? Just do it. Well, basically, Jeff, first you do it, and then you look at it. Thanks for that. What is the derivative? Cosine y times dy dx equals
1.
1. So dy dx equals 1 over cosine y. Now, sine inverse of x. So y is the sine. Where'd it go? I got it in here. So y is the inverse sine of x, right?
It's the angle.
So then now look at why I put that freaking bonus question on there, because this is going to immediately become important for you to know how to do. So really, how do I want this to be a function of x? I want it to be a function of x. I can get there if I just plug that in. What's the cosine of inverse sine of x? What triangle can I draw off of that? What triangle does that represent? X over 1, okay. Where's x? On the y side, and where's 1? And so what's this side?
1 minus x squared.
So what's the cosine of this?
That's x over r. Or so.
Be very specific. The cosine of that is?
Root 1 minus.
Bam. That's the derivative of the arc sine is 1 over the square root of 1 minus x squared. That's what it is. It's crazy. Did you expect it to be that? You had no idea what the hell it was going to be. And I don't blame you. You're not supposed to. Shit. So, did we expect that? No. Alright, so that was a little step. We got to get all the other inverse trig. I'm not going to make you memorize these, by the way.
Thank God.
Not too
Just because I don't have them memorized myself, I'm not going to make you do that. Okay, that's enough for today. So come see me if you need your test back. Anybody did get it? If you have a question.